In this set of lecture notes, we're going to continue looking at hypothesis testing when the mean, for the mean, excuse me, when sigma is known, and where I'm going to show you a second method for hypothesis testing that you could use instead. So the first method we did in part one was called the p-value method, which tends to be really nice because it does rely a lot more, or it can be used a lot more easily with technology. So we do tend to use the p-value method a lot. But there's also the critical value method, which is another one that we can definitely look at and utilize as well. So in the critical value method, it's really about the picture and drawing that bell curve and doing all of our shading. And what we're doing here instead is we're creating what are called rejection regions. So we're going to have these regions on the bell curve such that if our value falls in those regions, we're going to end up rejecting the null hypothesis. So another method to decide whether to reject the null hypothesis is to determine whether the standardized test statistic falls within a range of values called the rejection region. A rejection region, also called a critical region of a sampling distribution, is the range of values for which the null hypothesis is not probable, so it is unlikely. If a standardized test statistic falls in this region, then the null hypothesis is rejected. Now, remember, as we're hypothesis testing, we're always assuming the null hypothesis is true. So we assume that it's true, and then we look at the result we get. If we get a result that's unusual, so in the p-value method, that probability was very small. Here, an unusual value means that our test statistic falls in one of these rejection regions, then we reject the null hypothesis. So we kind of look at it like, well, we made an assumption that something was true, something really weird happened and unlikely, so we're going to assume that our original assumption was false. And that's kind of how these hypotheses work. So a critical value separates the rejection region from the non-rejection region. So again, we're using z values here because we're still in this section where sigma is known. So when sigma is known, we're looking at that normal distribution, that normal curve. So you're looking at z-scores or z values. So if you think when sigma is known, that tends to be our focus here. It's the same idea that it was in chapter 6 with confidence intervals. So how do you find the critical values then? And how do you find these rejection regions? So the first thing you have to do, just like before, is you really need to choose your level of significance alpha. So you need to choose that alpha value. And you also need to think about what kind of test is it? Is it a left-tailed, a right-tailed, or a two-tailed test? Then from there, we can go ahead and determine the critical values. So if you have a left-tailed test, you're going to find the z-score that corresponds to an area of alpha. If you have a right-tailed test, you need to find a z-score that corresponds to an area of 1 minus alpha. So basically, your alpha is on the right here, so the area on the left of that is 1 minus alpha. And if you have a two-tailed test, that alpha value gets cut in half, and half of it goes in each tail. So that's why you have these 1/2 marks here as well. And I'm going to do some examples so you can see what these look like and kind of see how to draw that picture. You want to definitely draw a sketch here. And again, draw a vertical line at each critical value to shade in the rejection region. So this is another section where really that picture is going to be really important. So just kind of quickly, if you're doing a left tail test, what ends up happening is, so we have our center at 0, here is your critical value, and your whole critical region here is on that left. Okay, so that is your alpha. If you have a right tail test, then what your picture ends up looking like, sorry about that guys, looking like, is that the alpha value is on the right. So you just want to be careful here. It just depends on what you're using. If you're using technology, then it doesn't so much matter where your alpha is. But if you're using the textbook, remember that in the table, you would need to look for the area on the left to find that cutoff value. So that's why it says 1 minus alpha, is because the area to the left is how you find that cutoff value. If you're using the table, or even if you're using inverse norm or something like that, right? And then the last one, the two-tailed, I'll do on this side. what ends up happening is you have one cutoff here, so this will be a C, or a 0, excuse me, and then one cutoff here, so that you have a little bit in both tails. Okay. And what happens is you have half of the alpha in this tail, and then you have half of the alpha in that tail. So again, when you're looking for those cutoff regions, you just really need to think about what's the area to the left here so that you can find those critical values. Now, if you have a two-tailed test, it is symmetric. So as long as you find one of them, you have the other one, just take the opposite sign. All right, so let's find the critical value rejection region for a left-tailed test with alpha equals 0.01. So again, I'm going to draw a picture every single time for these. I'm talking about z-scores here, right? So my center is going to be at 0. And it's a left-tailed test, so my alpha is going to be on the left here. So I'm looking for some negative z-value. I don't know what yet. It's negative because it's on the left of 0. And the whole area there is alpha, and our alpha is 0.01. Okay, so if it's a left tail test, the whole alpha is in the left tail. So you can do this with your table. Let me see if I can bring that table up really quick here. All right, sorry, the hardest thing I think is just all these video cameras and stuff. All right, so we're looking for, we said an alpha of 0.01. So in my table, I need to look for 0.01 to find that z value. So let's see. Looks like maybe right around right here, right? I see 0.0099, 0.0102. This one's a little bit closer. So it looks like my z value is negative 2.33. So you can find it using the table if you like table 4. And again, because the area is on the left, it's pretty easy to match up because again, the tables always give you area to the left. If you want to use your calculator, then what you're going to do here is you're going to use second, bars, and inverse norm. And again, it's going to be area to the left, your mean, and your standard deviation here. So our area to the left here is 0.01. Our mean is 0 and our standard deviation is 1. Again, when you have z values, your mean is always 0 and your standard deviation is always going to be 1 there. So let's check it on the calculator. So I'm going to hit second and then vars. And then I want inverse norm. The area here is 0.01. My mean is 0 and my standard deviation is 1. And you can see we get about negative 2.326, etc. So rounding that to 2 decimal places, we still get that critical value of negative 2.33. So here's that rejection value or critical value, and the one that's shaded in is your rejection region. So okay, so whatever you have shaded in there for that alpha, that is your actual rejection region. All right, let's do another example. So find the critical values in rejection region, this time for a two-tailed test. Okay. So I have a two-tailed test. So I have a critical value here and one here. They're going to be symmetric. So I kind of just need to find one of them. But you do want to be careful because I have two regions here, but my total alpha is 0.05. So you're going to take that 0.05 and you're going to cut it in half so that you can split that alpha. Okay, so you put half of alpha there and you put the other half of your alpha value there. Okay, so now we just need to find those critical values. And again, you can use the table or you can use your calculator. So if you want to use your calculator here, again, you're using second bars, inverse norm, and you just have to remember that you're doing the area to the left. So if I start with this one, my area to the left is 0.025, my mean is 0, and my standard deviation is 1. Now, you don't really have to do both sides because it's going to be symmetric, but I'm going to do it just to kind of show you how to check both areas. So this area to the left is 0.025. If I want to look at this area to the left, though, you do need to, oh, well, my markers are running out. Sorry, guys. You do need to be careful of how you're adding. So think about how much area is going to be to the left here. It's everything but this little piece, right? So your area to the left is 1 minus 0.025, which is going to be 0.975 here. So if you have something on the right tail, whether it's a part of a two-tail test or if you're just doing a right tail test, then when you enter your area to the left, you're really taking 1 minus that right tail because that will give you the whole area to the left of it. So for this one, we're going to put in that 975, and again, 0 and 1. And I should see the same values here, just one positive and one negative. So let's try that first in our calculator. So I have inverse norm. Okay, and then I'm going to put this one in first. So 0.025, comma, oops, 0.025, comma, 0, comma, 1. And I get about negative 1.96 here. And then for the other one, I have 0.975, comma, 0, comma, 1. And I have the positive version, about 1.96. So again, that's good. If you're not sure if you're doing it right, do both sides for a two-tailed test and make sure you're getting that same key value there, one positive, one negative. So my two critical values then are going to be negative 1.96 here and positive 1.96 in this case. Now, if you're using your table, you're just going to go obviously to your table in the back of the book. Let me try to bring this up again. So here again, I'm going to do the left side first. So the area that I'm looking for on the left side was 0.025. So I'm just going to go to my table and see if I can find 0.025. And I actually do get it exactly right here. And I can see my Z value is negative 1.96. So it matches the one that we just talked about. If I want to do this critical value, my area to the left is 0.975. So again, your table and that inverse norm only do area to the left. So I'm looking for 0.975 now, and I need to be on the positive side. So if I find that, I will see it right over here. And again, it lines up with 1.96 for our Z-score. So you can use your table or you can use your calculator to find those values. So that stuff we did back in chapter 5 really does come into play here occasionally when trying to find some of these key values or key probabilities.